Hi, my name is Can, and in this talk I would like to demonstrate a deep learning framework I've been working on called Exprgrad. Exprgrad is an experimental deep learning framework based on a custom differentiable programming language. Even though it is still in early development, all of the examples I'm going to show you in this talk already work. As a brief introduction to the framework, we're going to train a simple neural network to learn the logical XOR function. As you can see in this table, this function has two inputs and one output. The output is exactly 1 when the inputs are not equal. The architecture we're going to use is also pretty simple. We're just going to have a single hidden layer, 2 input neurons, 4 neurons in the hidden layer, and a single output neuron. We start by importing Exprgrad and the required layers. Next, we define the training data as tensors. The two tensors here are basically just the columns of the table from the previous slide. Now we define the network architecture. First, a dense operation with 2 input neurons and 4 output neurons is used to implement the connections between the input and hidden layer. We use a leaky ReLU as the activation function for the hidden layer. Next, another dense operation is used to implement the connections between the hidden layer and the output neuron. Finally, we use a sigmoid operation as a nonlinearity to constrain the output between 0 and 1. We use a mean squared error as our loss function and optimize the model with gradient descent. Now that we have defined the model architecture, it can be compiled to a trainable model. We will train this model on our training data for 5000 epochs. Finally, we evaluate the model on the input pairs to check if it produces the correct outputs. Until now, everything seemed pretty standard here for a deep learning framework. So what is so special here? To find out, we're going to look under the hood at how the operations we use to implement our network architecture are actually implemented internally. Let's start by looking at the sigmoid operation we used as a nonlinearity for the output. As you can see, the complete implementation is just 2 lines long. The main attraction here is the plus plus equal operator used in the second line. It is a macro provided by Exprgrad, which is used to succinctly express operations on tensors. The expression to its right is not regular NIM code, but rather code in a custom domain-specific language. Exprgrad is able to compile any code written in this domain-specific language to highly efficient machine code. This means that you can easily write your own operations for use within neural networks, without having to think about implementation details. The basic idea behind Exprgrad's domain-specific language is that you only have to provide a single layer definition, and the Exprgrad compiler will automatically generate all the required code needed for using your operation in a neural network. First, the Exprgrad compiler will automatically generate efficient machine code for executing your operation on the CPU. In order to use the operation in neural networks, we have to be able to backpropagate through it. The Exprgrad compiler is able to automatically compute the derivatives for your operation, optimize and parallelize them. In deep learning, we also want to be able to train our model on the GPU. To facilitate this, Exprgrad can also parallelize your operation and its derivative on the GPU. The most fundamental building block in Exprgrad is called a kernel. Here's a simple kernel in Exprgrad's DSL which multiplies 2 matrices. Every Exprgrad kernel consists of an output tensor, a main expression, and a series of loops. The loops are nested around the main expression. If we were to write this kernel in NIM, it might look like this. Exprgrad will automatically infer the shape of the resulting tensor and the iteration domains of each loop. It tries to choose the biggest iteration domains for which every tensor axis is still valid, and the iteration domains are independent of each other. With the inferred domains and output shape, the equivalent NIM code would now look like this. I would like to point out that this NIM code is just here for illustrative purposes. Exprgrad does not actually generate this code, instead it compiles directly to LLVM. Let's look at a few more kernels. Here's a kernel which transposes a matrix. Notice that the tensor indices here and here are swapped. This is what actually leads to the matrix being transposed. Here's a kernel which increments the value of each element in the input tensor by 1 and writes the result to the output tensor. In this example, we can see how we can use curly braces to directly access the elements of a tensor without knowing its shape. Here is a kernel which computes the sum of all positive entries in the input tensor. Here we use the select instruction to only add the positive entries to the sum. Let's create a kernel which just creates a tensor filled with ones. Our initial attempt might look like this. But if we actually compile this kernel, it does not work. Exprgrad says that there is a missing shape constraint for a tensor. This happens because the compiler cannot infer the shape of the result tensor based on just the kernel. Just given this kernel definition, it could in fact be of any shape. To solve this, we manually specify its shape using the with shape procedure. To build more complex programs, we can also combine multiple kernels. The simplest version of this is using the output of one kernel in another kernel. Here, the matrices A and B are multiplied with each other, and the resulting matrix is squared element-wise. It is also possible for multiple kernels to write to the same output tensor. Here we use this to implement a layer of a fully connected neural network. We first multiply the input by the weights matrix, and then add the bias values to the rows of the resulting matrix. When we compose many kernels to build complex programs, we actually build a graph, where the different tensors are connected by kernels. This graph is called a computation graph. Here you can see what the computation graph for the matrix multiplication and element-wise square example from before looks like. In this graph, we can mark certain tensors as input tensors. In this case, A and B are the input tensors. Tensors can also be marked as targets. By marking a tensor as a target, we can refer to it later and compute its value for a given input. Actually implementing this in code looks like this. First, we define the input tensors A and B. Then we specify how to compute the tensors C and D based on the inputs. This is done by simply specifying the kernels we discussed before. And finally, we specify the target tensors and compile the resulting computation graph to a model. Now we can compute the value of the target tensors for given input tensors by using the model.call procedure. You can see that we pass the values for our input tensors as a table literal here. Currently, the values of these targets are computed on a CPU. We might, however, want to compute them on a GPU instead, because it can greatly improve the performance of certain operations. Note that GPU support in Exprgrad is still an active area of development, however. So there are still quite a lot of limitations to what I'm about to show you now. You can compile your model for the GPU by setting the compile target parameter of the target you want to run on the GPU to compile GPU. You also need to pass a valid GPU context to the compile procedure. This allows you to select the GPU to use for executing the model in case your device has multiple accelerators. You can now execute the target just like you would if it was a CPU target. The input tensors will be automatically copied to the GPU, the target executed, and the result will be copied back to the CPU. To accomplish this, Exprgrad will internally generate a series of OpenCL kernels. In this simple example, the generated OpenCL code looks like this. If you've written any GPU kernels in the past, you will probably notice that this implementation is quite inefficient. Accessing global memory in kernels is usually slow, and this kernel does exactly that a lot. Instead, we would like to copy chunks of global memory to a shared cache to improve read speeds. To accomplish this, we can add a schedule to the kernel. A schedule is a list of directives which guide the compiler in optimizing the kernel. In this case, we will first tile the outer loops with a tile size of 16. Now we can cache the input tensors for each tile. Based on this schedule, Exprgrad now generates an improved kernel with a reduced number of reads from global memory. It caches chunks of the input tensors to local memory and then reads from these caches instead of reading the actual tensors. Since they are stored in local memory, reading from them is much faster. In a simple benchmark where I multiplied 10 pairs of 2048 by 2048 matrices, the total runtime went from 2 seconds without the schedule down to 850 milliseconds with the schedule. This is about 2.3 times faster. Exprgrad's domain-specific language is differentiable. This means that the Exprgrad compiler is able to automatically compute the gradient of kernels and computation graphs. Let's look at a few really simple examples of this functionality. We're going to start with a simple kernel which computes the square of the elements in the input tensor. When we evaluate this kernel for a range of inputs and plot the outputs, we get a parabola. By extending the computation graph by backwards pass and outputting the gradient for the input tensor x, we can compute its derivative. When we plot this target for a range of inputs, we get the following graph. As expected for the derivative of a polynomial of degree 2, it is a line. This also works for many different kernels. Here we can see a slightly more complex example. And here you can see that we can also differentiate select instructions. In combination with optimization algorithms such as gradient descent, automatic differentiation can be used to solve optimization problems in computation graphs. So instead of asking what the value of a particular target in the graph is, we ask what the value of a given input should be so that a given output error is minimized. In Exprgrad, an input whose value should be optimized to minimize such an output error is called a parameter. To demonstrate this, we are going to build an Exprgrad program which fits a polynomial to this dataset. I generated it from a parabola and also added some noise. Let's start by creating a kernel which computes the value of a polynomial for given values of x and a sequence of coefficients. We can now use this kernel to construct a computation graph which computes the values of the polynomial based on the input and the coefficients. The coefficients of the polynomial are a parameter to this graph because we later want to optimize them to fit the polynomial to the dataset. Initially, we start with a sequence of 3 random coefficients. If we visualize this polynomial in our plot, it looks like this. Because we chose random coefficients, it does not fit the data at all initially. The next step is measuring the difference between the current polynomial and the dataset. To do this, we are going to use a mean squared error. This basically just takes the average of the squared differences between the computed values in a dataset. Because our polynomial does not fit the dataset very well, the error is quite high currently. To reduce the error, we are going to use Exprgrad's automatic differentiation capabilities. First, we compute the gradient of the coefficient tensor with respect to the output error. And then we use gradient descent to reduce the output error. After doing this once, the polynomial already looks a bit closer to the dataset. Repeating this for a few epochs results in a nice model for the dataset. This approach of using gradient descent to minimize an error by optimizing a set of parameters to a model is actually something we've done before. In the beginning of this talk, I demonstrated how to implement a basic neural network for learning the XOR function. Here is the code we used to construct this computation graph. If we draw this graph, it looks like this. Each layer has weights and biases parameters, which are optimized to minimize the mean squared error between the expected outputs and the current output of the network. This is the general approach we take to solve optimization problems, such as the training of neural networks. So even though I call Exprgrad an experimental deep learning framework, it is really meant for solving a much larger class of continuous optimization problems. There are actually a lot of cool things we can do here. One problem I personally find quite intriguing is called inverse rendering. Rendering is the process of converting a scene description to an image. The process of inverse rendering is the opposite to this. We get an image and we want to recreate the scene description from it. This problem can be formulated as a continuous optimization problem. We start with a guess of what the scene description might be and render an image from this guess. Now we compare the rendered image with the target image. And finally update the scene description guess to reduce the error or difference between the rendered and target image. This diagram I've drawn here is basically already our computation graph. The difference between the two images is the error we want to minimize. The scene description is a parameter and the target image is an input to our graph. To be able to render an image from a scene description, I've implemented a simple 3D ray tracer in Exprgrad's domain-specific language. This here is actually the complete source code for its kernel. Since Exprgrad can compute derivatives for the renderer, we can backpropagate through it and use gradient descent to optimize the scene description. Here is a simple example where we optimize the material of two spheres to match the target image. On the left side you can see the current guess, and on the right side the target image. As we run the optimizer, the difference between the two images decreases until the scene is nearly perfectly reconstructed. The neat thing is that we did not have to implement the actual inverse rendering function itself. Instead, we just specified how a forward rendering function works and used Exprgrad's automatic differentiation capabilities to optimize the input. Now that you have an overview of the capabilities of Exprgrad, I would like to briefly show you how all of this actually works. To demonstrate some of the key steps, we will follow the process of compiling this basic matrix multiplication kernel. First, the kernel is converted to an abstract syntax tree by expanding the syntactic sugar using the ++ equal macro and then tracing the applied operations using operator overloading. This abstract syntax tree is then flattened into Exprgrad's intermediate representation. This is what the intermediate representation for the matrix multiplication looks like initially. The intermediate representation is a register-based IR. All program transformation and analysis passes performed by Exprgrad operate on this intermediate representation. Each target in the computation graph gets flattened to its sequence of kernel executions. Each kernel consists of a set of outer loops and conditions, a set of tensor reads, the main expression, and an output tensor. In this case, we have three outer loops: read from the inputs tensor1 and tensor2, compute the product of the two reads, and write a result to tensor0. All program transformations and optimizations by Exprgrad are performed on the IR. Exprgrad currently runs 27 different passes on each program. The code which actually runs all of these passes can be seen here. Each line corresponds to some program analysis, transform, or optimization which is performed. For example, the infer shape constraints and sort shape constraints passes are responsible for inferring the shape of the output tensors. The generate pass is responsible for computing the derivatives of kernels. Exprgrad uses reverse mode automatic differentiation for this purpose. The identify independent pass identifies loops which could be automatically parallelized. After reorder loops chosen optimal loop ordering, the choose parallel pass selects which of these candidate loops are actually parallelized. After applying the program transformation passes for compiling to the CPU, the resulting intermediate representation for our matrix multiplication example looks like this. Among many other optimizations, the loop order has been optimized by reorder loops. The shapes and loop bounds have been inferred by infer shape constraints, and the tensor accesses have been converted to reads and writes to or from memory by inline tensor operations. This transformed intermediate representation is now compiled to the LLVM IR. LLVM now further optimizes the program and compiles it to machine code. Exprgrad uses LLVM's JIT compiler to run the generated code. Now we have a basic overview of the capabilities of Exprgrad and how it works internally. Of course, Exprgrad was not developed in a vacuum. It borrows many successful concepts from other array and differentiable programming languages. Here are some of the inspirations and references for Exprgrad. As I said before, Exprgrad is still in early development. So what is next? Here are some active areas of development. Currently, it is impossible to represent loops with dynamic iteration counts in computation graphs. My current plan to solve this is by moving away from a pure graph representation of targets and instead using a Turing-complete single static assignment representation. This would allow the conditional execution of kernels as well as representing loops while remaining fully differentiable. Much of the work to date had a focus on building an architecture for Exprgrad which enables large impact optimizations such as automatic parallelization and shape or cache inference. I've neglected implementing many more specific optimizations as well as fine-tuning the automatic optimizer. So there is still a lot of work to be done here to match the performance of other deep learning libraries. And of course, as I said before, GPU support is also still in active development. If you have interest in helping out with any of these tasks, please open an issue on the GitHub repository. If you are interested in Exprgrad, you can check out the GitHub repository linked here. And if you have any questions, you can either reach me on the NimScience channel or on any of my socials. Thank you for listening.